Today we're going to begin looking at negative feedback. Feedback is generally characterized by the type of connection at both the input and the output. There are several different types of feedback. We have voltage and current feedback, and we can relate these to their connections at the input and the output. For instance, for voltage feedback, we would place a series connection at the input and a shunt connection at the output. For current feedback, we would do the opposite. We would use a shunt connection at the input and a series connection at the output. If we think about this, this is because for a voltage amplifier, we know that we want a high impedance at the input, and series connections increase impedance. At the output, we want a low impedance, and shunt connections decrease impedance. Vice versa for current. Generally, feedback is classified by the connection at first the input and then the output. And so we would label feedback by these connections. For instance, a series amplifier means that there's series connection at the input and series connection at the output. This type of amplifier is used for a transconductance amplifier. A transconductance amplifier is an amplifier that takes voltage as an input and delivers current as an output. We'll examine this in a later set of slides, but for now we use Z parameters when we're analyzing transconductance amplifiers. We'll examine what that means shortly. Series shunt amplifiers are voltage amplifiers. These are the amplifiers that we've seen thus far in the class. These use a two-port network parameter called the H parameter. Again, we'll examine that in a later set of slides. Shunt series amplifiers are current amplifiers. These amplifiers use what are called G parameters. And finally, we have shunt-shunt amplifiers. And shunt-shunt amplifiers are transresistance amplifiers. Transresistance amplifiers take a current as an input and output a voltage. And these amplifiers use Y parameters for their feedback analysis. Now, feedback affects the bandwidth. We've already seen that feedback increases the bandwidth by a factor of 1 plus the loop gain, but it also has an effect on the input and output impedances of the total circuit. Shunt feedback serves to reduce impedance, and it does so by a factor of 1 over 1 plus the loop gain. Whereas series feedback increases impedance by a factor of 1 plus the loop gain. In the next set of slides, we're going to examine two-port network parameters so that we can use them in our feedback analysis to come.